We are now going to look into a very simple and straightforward problem of using finite volume method. We have discussed at length about the method and its formulation for Maxwell equation. It has been very well tried and tested for various applications, and I have shown you some of the applications over the course of the lectures. We looked at spiral antenna simulation, we have looked into waveguide simulation, and we have also looked into perfectly matched layer applications in finite volume method. So now, using a MATLAB example, I wanted to see how the simple problem such as a hyperbolic problem can be formulated, and we can test one of the problems that we normally come across, the hyperbolic formulation, which is a heat conduction problem, and see how this problem can be modeled using finite volume method. So let us look into the basic equation that we are interested in, which is the hyperbolic equation. So the hyperbolic equation in general will have the form dou u by dou t plus divergence of a flux function is equal to 0. And of course, there will be a parameter alpha, that is a parameter that we multiply. This is the general formulation of the hyperbolic form, but let us take the conservation law. So hyperbolic forms are related to conservation law, and Maxwell equation can be casted in this particular form, but let us take a simple one dimensional form so that we will understand how this form can be applied for simulating a problem on MATLAB. So let us start with a problem where we have only one dimension. So we will have dou u by dou t plus dou of the flux function, let us call this flux function as C, by dou x is equal to 0. So there is a relationship between these two terms. So this is the flux function, this is the divergence of the flux function, where the flux function f of u is equal to C. Once you have this, we can write them in the integral form, integrating along the domain. If you integrate it along x, so x goes from x of a to x of b, we have dou u by dou t dx equal to, so we have a minus sign that is coming, which is minus of the flux function integration. So integral of x a to x b dou phi by dou x dx. This can be simplified into, that is equal to minus sign outside, we will take phi u of xb minus u of xa. So this is the value. So now we are going to use the midpoint rule so that we can apply certain algorithm for the left hand side term as well. So let us take it further. So what we have got here is integral xa to xb dou u by dou t dx equal to minus phi u of xb minus u of xa, and this particular left hand side term can be simplified further by using the midpoint rule, and the midpoint rule will give us xb minus xa dou u star by dou t is equal to the same thing that we have on the right hand side. So if we choose the control volume such that So if you choose the control volume I minus half delta x comma I plus half delta x. So this is the control volume. So if you take a line like this, and let us say this is I minus half, this is I plus half, this is I plus 3 by 2, so on and so forth. The control volume I is going to be centered exactly at I and I plus 1, so on and so forth. So these are the central control volumes, and where, so if you say this is the control volume and we have the center of the control volume at I delta x, and if we say delta x is equal to h, we say I times h. So this is the way we structure the control volumes. Control volumes will have the values stored at the center here, and we can approximate the value at the edges using a very simple approximation, that the value u star, what we have here, is going to be the value at the center itself. So if we say u approximately equal to u star, so this is the approximation that we are using, and once we do that, we can use this information to compute the right hand side. So this is the information that we will use to compute the flux function, whereas we will keep u as u itself on the left hand side. We will see how we do that step by step. So what we have is xb minus xa multiplied by dou u by dou t is equal to minus the flux function at u equal to xb minus u of xa, and for this we are going to use the approximation u star is approximately equal to u, and xb minus xa will be given by delta x, which is equal to h. So when we rearrange the term and use the forward differencing for time derivative, what we get is u of I n plus 1 minus u of I n divided by delta t is equal to minus 1 by h. So I have taken the h on the other side, multiplied by the flux function at x of, so I plus half minus the flux function defined at x I minus half. So I have to close the bracket. So this, if I rearrange it a little bit, what I will get is u of I n plus 1 is equal to u I of n plus, the minus sign is there interiorly, so I will put minus delta t by h and the flux function phi x I plus half minus phi I x I minus half. And for computing the value at phi at x plus half and x minus half, I use this approximation, which is the flux, the field value at this point at I plus half and I minus half is going to be given by the value of the flux at center itself. So this is a very crude approximation. We saw during the Maxwell equation problems that we can go higher order in approximating the flux functions on the surface using either muzzled method or the method of weighting. So this is a very simple straightforward approach which works fine for simple problems like heat conduction problems where dissipation is not an issue, so we can still use such an approximation. So what we get essentially is u of I n plus 1 is equal to u of I n. So I will take the minus sign which was here outside and write it directly using the minus sign. So I will have minus delta t divided by h. I will simplify it saying phi of u of I minus phi of u of I minus 1. How did I come to this point will be clear if I once again show you the stencil here. So the flux at I plus half is going to be directly given by the value of u itself, u at I. So that is what I have written here, u of I. Whereas for this u, this I minus half, the value at this point will be given by the cell that is sitting here. We have not written it, but this is going to be the I minus 1. So that will give me the value of the field here, this will give me the value of the field here. Similarly, this will give the value of the field here, so on and so forth. So this is the way we are computing the value. So I minus 1 will contribute to I minus half, I will contribute to I plus half, I plus 1 will contribute to I plus 3 by 2. So the value at the face centers or face, here the faces are nothing but the end of each of the elements in one dimension. In 3 dimensions you might talk about the face centers using the triangles. So the value at this face center, the value at this face center, the value at this face center. So this will be the 2D case, but in the 1D case you are talking about face centers as the end of the edges. So the value at this point is going to be the value at this point, and the value of the neighboring cell, the cell before, will contribute the value here, so on and so forth. That is why we have I minus 1 here. And if we can simplify the subscripts a little bit and write the value of the flux. So flux of u of I is equal to C multiplied by u of I, where C is the propagation velocity of the solution. In Maxwell equation, the C will be the velocity of light itself, the velocity of electromagnetic field that is propagating, whereas in this problem more general C will be the velocity of the solution propagation, so Ui's propagation. So if we use this notation, we can simplify this equation even further as u of I n plus 1 is equal to u of I n minus C delta t divided by h multiplied by u of I n minus u of I minus 1 n. So what is beautiful about this equation is the terms what we have on the left hand side are using n plus 1, whereas the terms on the right hand side are having values only at u of n. So this is an explicit formulation. And of course what we have also is there is a condition of CFL which says 0 less than C delta T by H less than or equal to 1. So this is the CFL like condition. So this is for stability, and this is the value for the flux function, and this is the final formulation that we have. With this background, we are going to study a simple problem using finite element method. The problem what we are going to do is a heat conduction problem, and the formulation or the equation of the problem is going to look like this. So we will have d dou u by dou t is equal to k some constant multiplied by dou square u divided by dou x square. So this is a problem where we are going to use finite volume method, and we are going to compare it also with the finite difference method that we studied before, because there is a lot of similarity. At least on the one dimensional problem you will see the finite difference and finite volume will have some similarities and some differences. So let us take this particular problem, and the problem has certain boundary conditions and some initial conditions. The initial condition is u of x comma 0 for all x at time equal to 0. The solution is going to have the following relationship. So u of x is equal to 0.1 sine 4 pi x by L. L is the length of the domain. So we go from 0 to 1. So L will be equal to 1. And what is also important to know is there is a boundary condition which is nothing but u of 0 comma t is going to be 1 and u of L comma t that is going to be equal to 0. So L is equal to 1, so we can write u of 1 comma t is equal to 0. So if you look at this problem, what you will have is some initial condition, certain patterns. The pattern is going to have 4 pi x by L as the value. So if you look at it and try to draw it, so if this is x equal to let us say 1 and x equal to 0, at x equal to 0 the solution is going to have a value that is equal to 1. So if you say this is 1, so it is going to have a value 1, but it is also going to have some repetition because it is a sinusoidal function, and it is going to have a value of 0 at the end, and the in between 0 and 1 it is going to go through certain parameters. So if you put x equal to 0 in this, what you will get is a value 0, but it will also have a value that is 1 because it has been set as 1. So this is the boundary condition, this is the natural condition in which it propagates. So let us see how we can simulate this problem using finite volume. So for that we have to start with discretizing the left and right hand side. What we will do is we will do central differencing both for the time and for the spatial derivative. So what we have got for dou u by dou t using the central differencing will be u of n plus 1 minus u of n minus 1 divided by 2 delta t. This we know from our finite differencing method modules, and when we want to do the same thing for the spatial derivative but with the second order, this is going to be given by u of n I plus 1 minus 2 u n of I plus u of n I minus 1 divided by h square. This is central differencing in space, and what we are going to do is we are going to substitute for this one using averaging. So what we are going to do is basically we are going to say u of I of n is going to be given by u of n plus 1 plus u of n minus 1 divided by 2. So I am taking the old value, which is u of n minus 1, and the current value is u of n, the future value is going to be u of n plus 1. So I am taking the old value plus the new value divided by 2. This will give me 2 u I of n is equal to u of n plus 1 plus u of n minus 1. So this is what I am going to substitute into this equation, which will get transformed into a different form, which is nothing but u of n plus 1. So I am substituting the value for the left hand side as well, u of n minus 1 divided by 2 delta t, that is equal to u of I plus 1 of n minus u of n plus 1 I plus u of n minus 1 I. This is what I am substituting here. So this should have I, these are the subscripts. So once I substitute that here, what will happen is I will have these two terms here, and then I will have the last term unchanged, u of n I minus 1 divided by h square, and if I rearrange it and keep only u of n plus 1 of I, so there is another term of u of n plus 1 comma I here. So when I bring them back all in one side, what I will get is u of n plus 1 of I equal to 1 minus beta divided by 1 plus beta of u of I n minus 1 plus beta divided by 1 plus beta of u of I plus 1 of n plus u of n I minus 1, where beta equal to 2k delta t divided by h square. K is the constant that we had in the starting of the equation, and this is the way the beta is calculated. So there is a lot of similarity between this approach and finite difference approach, and of course these are some differences. The differences are nothing but the way we are computing the fluxes and how we are approximating the fluxes. But now let us look into the program itself and see how the initial value and final value are being replicated. So this is the program. So I am going to run it for 150 steps. The parameters are L equal to the domain length, K is the heat diffusivity, I set L equal to 1 and K equal to 1, and the other parameters dx is equal to L divided by n minus 1. So this is going to be the h value as well, and dt is going to be dt is equal to twice the dx square value, and we are setting the initial profile q equal to 1. So I said the value is going to be 1 for x equal to 0 and 0 for x equal to 1. So these 2 points are fixed, and in between it is going to have a sinusoidal variation, and L we have set it to 1, so it is going to be 4 pi of x. So it will have some kind of and at this point it is going to be equal to 0. So if we are simulating this problem and we are going to see what is going to happen, so go back to the code, what we see is we are setting the values for the initial profile, and this is going to be the value that we are giving, and we are trying to plot the initial value and also the computed value. The computed value we are using the method called as Dufort-Frankel scheme, and Dufort-Frankel scheme is nothing but the method that we have used here. So this is the for u of n Dufort-Frankel scheme. Substituting for u of I of n, we are substituting the value that is average of the two time step values. So that is what we have done here in the code, and we have set the boundary condition to be equal to 1. The boundary condition at u of n, which is the last point, is going to be 0, and the value of the updated equation is also going to get plotted. So initially we will have v initial, which is going to be given by the dotted lines, and then we are going to plot the updated equation. So what we will see is the wave heat conduction is going to move, and we are going to plot the value of the u at time step t equal to 0.03, which is nothing but this delta t multiplied by the number of iteration we are running. So number of iteration we are running is 150. So if you do 150 multiplied by delta t, you will get that. So let us run it and see what is happening. So this is a dashed line. You see that the value is 1 initially, and then it goes to 0, and you see that the value of the computed solution after the time step is 150 steps forward. We say that it is propagating in this manner. So if we can rerun again, you will see, maybe I have to rerun it with a little bit more time pause. So let me put time pause is equal to 0.001. Maybe I will reduce the time step even further. I am reducing the pausing between the simulation even more. So this is the way the heat conduction is going to propagate, and the initial values are given by the dotted lines, and then the final value is given by the solid line at time step 150. So this is a very good example for you to try, and the source of the code is from this book, An Introduction to Computational Engineering with MATLAB. I encourage you to practice coding in 1 dimension and 2 dimension, which will be very good for you to understand the methods, mathematics, and also the complication. It is not good to go directly to a 3-dimensional problem and code it. So we have tested finite volume method both using a 1-dimensional problem like a simple heat conduction problem, and I also shown you earlier some of the problems that we simulated using finite volume method, like the horn antenna or the spiral antenna or the waveguide truncation and the PML applications. So in that way we have covered quite a bit of simulation using finite volume method. So I encourage you to program your own code for at least for 1-dimensional problems, so that you get to know the method more and more closely, and you can differentiate various aspects of the method from paired to finite element method or finite difference method. That way you can master the technique and also know when the method can be applied and when not. Thank you.